Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. The last class we have seen how to you can say generate Jacobian matrix, and as well as how to actually obtain velocity for different joints starting from 0 to the end effector. We call base to E, which we simply call velocity propagation model. So this is what we have seen, and in the end of the lecture itself I said we would be seeing the same thing can be used in Matlab as an efficient tool with a simple symbolic math code, and we can see that in this particular lecture. So in that sense, what we are trying to do is actually we will take a same example which we have seen in the last lecture, the 2R serial planar manipulator we will take, and then we will derive it that in Matlab and see whether the same equation which we obtain in the analytical method we are getting into Matlab or not. So for that, first we will recall. So the 2R serial manipulator is having two rotary joints. So these are the you can say rotation matrices and the position vectors. So based on this, if we take base velocities are 0, both you call angular velocity and as well as you call linear velocity, both are 0, then you can actually propagate the model based on the angular velocity propagation system. So in that you can actually start omega 1, omega 2 and then omega 3. So similar way we can actually start with the linear velocity propagation model, and where we start from the linear base velocity 0, and then we can actually propagate V1, V2 and V3. So once we obtain, we can actually see we can get to the what you call end effector velocity with respect to you can say base frame, in the sense velocity of 3 with respect to what you call 0th frame, we can actually see it here. So in that sense, what one can actually find, so this will give a Jacobian matrix, that is also we have seen in the last class. So now the same thing, can we do it in Matlab in the same format? Yes, we can do it. So for that, if you use the live script, even it would give in a symbolic manner, but we are not actually doing it live script. We would be using a simple math script. So we can actually see Matlab script code. So for that, I am actually showing the code here. So these are the velocity you can say kinematics which we are trying to do it. So for that, we are taking the rotational matrices and position vectors which we have obtained from the previous you can say simulation code. We can actually obtain, where A would be the cell that would be having 3 cells. So each cell would be having a rotation and rotation matrix and position vectors. So from there you can take, for example, if you take A1, which is the first cell, the first 3 cross 3 would be corresponding to the rotational matrix, and the next you can say 3 of the 4th column would be equivalent to position vector. This is we all know. So the same way we can actually do it for the second cell and the third cell. So now what we have done, so previous code we have taken, and from that we can find the rotation matrices and the position vectors. Once we obtain this, so what we can do, we can actually do the angular velocity propagation, where we can actually see there are 2 additional variable would be coming. Virtually these are actually theta 1 dot and theta 2 dot. So here we cannot write theta 1 dot, theta 2 dot. I have written th1 dot, th2 dot. So both are I represented as real. And further what we have taken that the base angular velocity would be starting from 0 because it is fixed. So in that sense, omega 0, which I have written as w0 equal to 0 0 0, in the sense 0 you can say zeros of 3 comma 1. So now once you obtain this, what we can do, we can actually substitute the velocity propagation model, where omega I plus 1 to I plus 1, which we can write as r I plus 1 to I omega I to I plus, so the active variable addition. In this case, so we have already know the rotation matrix, that transpose would be coming here because it is inverse, and omega 0 is known, and this is the active joint. So theta 1 dot is added, which is actually third quadrant, third element in the sense z axis. So this will give omega 1, which I have written as W1. So similarly, we can calculate W2 and W3. Once you obtain W1, you can calculate W3, and you can actually like calculate W, you can say 2 and 3 through this sequence. Once you obtain, what one can do, so this is equivalent to omega 3 with respect to third frame. So in that sense, you can actually like calculate what you can say, so the omega 3 with respect to 0. So these are the things we are actually like trying to see it in Matlab. So let us go one step further. So what we can do, we can actually like try to understand the linear velocity propagation. So for that, again the base we are starting, the base it is fixed, so the linear velocity would be 0 0 0. If it is put it on the mobile base, then this would come with the mobile base velocities. So once this is all done, so we can go the velocity propagation model where the slip velocity and tangential velocity would be coming. So once you calculate this, so V1, then V2 and V3 we can calculate. Once you calculate V3, you can get the V03 in the sense, so velocity of third frame with respect to 0th frame we can actually like calculate. So here the simplify command is just to simplify the overall equations. So okay, so now we will actually like see this further. So once you obtain this, what one can do, we wanted actually like Jacobian matrix, which would be, you can say, coefficient of your you can say theta 1 dot and theta 2 dot. So this coefficient we can use a simple Matlab command called equations to matrix, or once you know the position vector from the forward kinematic model, you can do the partial differentiation with respect to q vector. So that is what we have done here. So now we have all seen so how the Matlab code look like in a slide format. We will go to the original Matlab code. Okay, so this is the direct kinematic you can say code which we have done in the previous simulation class. So this is the, you can say, the generalized variable, and variable based on the DH table we have actually like given, and here the number of joints are actually like including, you can say, end effector it is 3, but excluding the 0th frame. Then the DH parameter as per the table which you are derived, that we can substitute, and the arm matrix we can actually like get it. Here we are going to use the non-standard one. Okay, so these all we have seen. So based on that, what one can see, you can actually create A would consist of 3 cells. So each cell would be having a transformation matrix. So these all we have seen in the previous simulation class. Right now what we are taking, so we have taken the P for the Jacobian, but right now we are trying to see the you can say velocity propagation model. So for that we are actually like coming to the velocity kinematics. So till last simulation class we have ended at this end. So we are adding the code whatever I have shown in the slide here, from starting from here. So this is the velocity kinematics. So for starting the velocity kinematics, you need to know the individual rotation matrices and position vectors. So this we can get it from the, you can say, cell which you have created in the previous direct kinematic model. So these all we have obtained. So in this case, rotation matrix of 1 with respect to 0, 2, rotation matrix of 3 with respect to 2. Similarly, the position vector 1 with respect to 0, 2, position vector of 3 with respect to 2. So these all we obtain. So then we are actually like going to the velocity propagation. For that we need to create a variable. So here there are two active variables, which is theta 1 dot and theta 2 dot, which we have written as theta like th 1 dot, th 2 dot, which we consider as real. So now this is the, you can say, code which is actually like taken from the velocity propagation. So once you have the angular velocity 0th frame is known, then you can calculate the further proceeding frames 1, 2, 3 and all, right. So this is the code, and we can find the end effector angular velocity. Okay. So then we can go to the linear velocity propagation, because the linear velocity propagation required both you can say previous frame linear velocity and angular velocity and position vector. Position vector, by the way, we got it from the direct kinematic model, but the angular velocity need to be calculated. That's why we have calculated already. So now we can actually like do the linear velocity propagation. So these are the propagated model. Since in this particular example there is no linear joint, so everything is rotary, so there is no addition of d1 dot, or you can say d1 I plus 1, that is we are not added. So finally you can calculate 3. So with respect to base also you can calculate. So now this is what the end effector linear velocity with respect to base, in the sense the end effector velocity which is here as a third frame, that velocity with the 0th frame you can calculate, which is as equivalent to px dot, py dot, pz dot. So since it's in a planar, the pz dot would be 0. So we can actually like take from there, I already said. So the command called equations to matrix, we can do it. So where v03 is the final end effector velocity. So I want to get it that partial derivative, so I can take it a coefficient. This is one way, or the other way, right? You can do it method through partial derivative. Okay. So we'll actually like go one by one. Okay. So as I already said, I have actually like minimized this editor window. So you click the editor window and you can run this code. So this code is actually like you can say error free. So now if you run this code, you can see that the result would be obtained here. Okay. So we can actually like start from this. So these all we have seen in your kinematic model. So up to what you call approach. We'll start from what you call omega 0. Omega 0 we have actually like, I'll put it. So omega 0 we have considered as 0 0, right? So we'll actually like see what is omega 1. Omega 1, which we got it from the analytical model, is so 0 0 theta 1 dot, whether we are getting it or not. Yes, we are getting it. So similarly omega 2 would be theta 1 dot plus theta 2 dot in z axis. So that is also we obtain. The same as you can say omega 3, right? Because it is the same link, that is also we obtain. So now we can actually like see what would be the end effector. So end effector also it is straightforward because it is actually like simple, but you have a rotation matrix. If the theta 1 and theta 2 are non-zero, then that also will play, but in this case I don't think that would be having a play. Why? Because your rotation matrix would be so cos theta 1 plus 2 theta 2. So like that it comes. So this all you can say thetas would be in x and y, but your omega 3 is having x and y is 0 0. So that's what you can see. So in the sense, so the third frame you can say z axis and 0th frame z axis all are parallel. So in the sense, whatever you have the third frame velocity, that would be directly transformed to, you can say with respect to 0th frame. So this is correct, you got it. So this is we have verified in the analytical also giving the same. So we start from V1. So V0 we assumed as 0. So V1 would be what we expect, because 0 and 1 on the same point. So there would be 0 linear velocity. That is what we have seen in the analytical also. So here also the same. But when you come to the second, you can see, right? So there would be L1 distance and the tangential velocity would be coming. So that would come here. So if you put theta 2 is 0, so what you can see, if you put theta 2 0, so it is actually like velocity would be only in y axis. That is very clear, right? A1 theta 1 dot would be the magnitude, that would be direct parallel to y axis. So that is actually like visible here also, right? And x axis 0 velocity, that is also clear. So now you put theta 2 is 90 degree. So you can see in that case, so theta A1 theta 1 dot would be having perpendicular, which is actually like approach side. So that is also right. So A1 theta 1 dot would be there. So in that sense this direction, but if you take it from 0th frame, that would be a negative direction, that you can actually like cross check it. Okay. So let us actually like go to the V3. So V3 would be added. So I will actually like show it clear. So these are the V3 components. So you can see now the V3, the x axis one velocity added, but y axis you can see something is addition. Okay. So this is all actually like with respect to something, but what we wanted, so V03. Okay. So V03 is actually like what you wanted. So this is having actually like a lengthy equation, right? So but this lengthy equation you can actually like reduce it to a simple one. So for that what we are trying to do, the Jacobian, right? So you can actually like see the Jacobian. So Jacobian you can actually like get it. So you can actually like see this is A2 sine theta 1 plus theta 2 minus A1 sine theta 1. This is what we also obtained in the earlier one, and here also you can see this is A2 sine theta 1 plus theta 2. Okay. So the minus sign, it is very clear. So similar way you can actually like see in the x and y. So in that sense I want to show like this is the first component. Okay. So I'll just make it, this is the first component. Okay, you can actually like see first component is having, so theta 1 dot is having, you can say 2 places, right? Theta 2 dot is having 1 place, right? So that is what we can actually like see it as a Jacobian. Okay, the same thing you can expect in J1 with the partial derivative also. So that is what we have actually like obtained, right? So you can see this is also the same case what we have seen. So in that sense, what one can actually like clearly see, so whatever you have done in analytical, the same thing you can port it as a code in Matlab and do it. Even this can be even further simplified as a simple generic code, but that is actually like a little complex to understand. So that's why I have written this code as a lengthy one. So instead of this omega 1, omega 2, omega 3, I can put a for loop. So where I can actually like for loop will start from I equal to, you can say 1 to n, and inside I'd say that whether it's a rotary joint or prismatic joint, I can put a condition. So based on that I can actually like iterate and then I can do it, but that would give a confusing end to you. So I have actually like written in a propagated way. Okay, some people will say that it's a recursive one, why you have done in a sequence, just to give a clarity. The same thing can be realized in you can say other one in the sense we can go another example. Okay, you can see that is also like seen in the forward kinematic model or direct kinematic model, where the 3R serial robot we have seen, sorry, this is actually like RRR. So this serial robot we have actually like seen, it's a spatial. Okay, so this robot we have seen, this is the DH table, and these all we have seen in your previous simulation you can say lecture. So now we will start only from here. You can see this is the same thing, what only one thing is added, the rotation matrix of the fourth frame and the position vector added. So similarly one additional active variable which is theta 3 dot, that is added, and here you can see that we have actually like extended up to omega 4. Okay, so since we have extended, so this end effector velocity is actually like omega 4 with respect to 0, that is what with respect to base frame. Similarly the linear velocity is extended up to this. Okay, so this also we can extend, since we know this method also giving the same result. So I did not actually like what you call did the second method, the J1 I calculated in the earlier code, that is I did not do it. So now if I run this, obviously this will give the right result. You can also like verify, and I will be sharing these codes in your lecture material, so you can actually like find it. So now this was run, and you can actually like see these are, you can say, your normal sliding and approach vector, and this is what the Jacobian, and you can see this is what omega 1 and this is the omega 2. Okay, so here it is the first joint is vertical rotary and the second joint is actually like planar in the YZ plane. Okay, or you can say XZ plane, whatever plane you consider. So in that sense you can see that there is a angular velocity, this is actually like theta 1 dot here, but when it comes to this axis, so it would be having a transformation, that is what you can see it from this result. So similarly omega 3 it would be parallel, so you can see that just added, and the what you call the coordinate would be added. Okay, so that is what, if you look at it, the third component of omega 3, you can see it is theta 2 dot plus theta 3 dot. Why it is so? Because the axes are parallel for 2 and 3. So the same sense, if you go for omega 4 you can say 3, so that is also same, because the third frame and you can say fourth frame are the same link, and the fourth frame is not having any active joint. Okay, and we have assumed that both axes are parallel. The same sense we can actually like start, we assume 0 v1, so we because both are actually like same point, and v2 you can actually like see 0, because in this case if you recall RRR 3R manipulator, so the first axis comes here, second axis goes inside the, you can say, picture or inside the screen. In the sense 0, 1, 2, 3 all actually like having in the same line. especially 1 and 2 are having the same point. 0, 1 are actually like d1 distance, but the d1 distance is constant. So there is no linear velocity happening at, you can say, 0, 1 and 2. That's why you can say up to V2 it is having 0. When you come to the third, so V3, you can see like the tangential velocity is coming. Here only tangential component will come because we have considered all our rotary joint. So probably one additional example I may put it somewhere in the middle. So you can see if the prismatic joint comes, how it will come. Okay. Anyway, in dynamics we would be seeing that in a prismatic. So we can actually like try. So similarly V4 you can actually like see. So V4 would be lengthy because it is having a connection. So V4 of 1, sorry, V4 of 1 you can see this is. So V4 of 2 you can actually like see it that way. So like that you can actually like see it would be expanded, and now you can actually like find the J. So J would be a small extension of the other one. This can be obtained with the same thing. So for example, J of 1 comma 1, I'm just showing it. Okay. So I'll just make it this. So J of 1 comma 1 and differentiation of, so P of 1, okay, comma, so theta 1 would be the same, right? So but I did not simplify, so that's why it is actually like coming slightly different, but you can see like these two are actually like same, right? So that's what we can actually like see it. So in that sense, I am actually like ending this particular lecture. So where we have seen like how to do the velocity propagation model of a serial manipulator with the help of Matlab. So this code is actually like very generic. You can just you can say put it, as long you have a direct kinematic model which you have written in Matlab. It is simple extension. If not, you should have a rotation matrices and position vectors in your hand, and then you can actually like make the propagation model. So either way you can do it, but I already did the direct kinematic model in Matlab. I just extended. Otherwise you have to write the rotation matrix then and there. Okay. So that's only a thing. And please make sure, so when you are calculating omega I plus 1 with respect to I plus 1 frame, so the rotation matrix is a, you can say, inverse or transpose of the normal matrix, in the sense, so when you calculate omega 1, so the rotation matrix is actually like 0 1 transpose, or you have to write R10, that is we don't have, so we are taking a transpose of R01. Okay. So that make it clear. So with that we are ending this particular lecture. The next lecture would be talking about the statics and you can say singularity of the serial manipulator. So we can actually like see. Until then, thank you. Bye. See you then.